Some electromagnetic radiation principles. This is a short PowerPoint that runs through a few of the fundamentals in a little bit more depth than we have in Remote Sensing 1. And so one of the things that we have to be concerned with when we're measuring EMR is the notion of error. And so we're really, in remote sensing, we're most concerned with two main types of error, radiometric and geometric. And of course, radiometric correction. This is one of these types of error that we do some corrections on, particularly when we're doing change analysis, the angle of incidence or the seasonal correction that we do. Geometric correction is applied really before we get the data. If you've ever worked with raw remotely sensed images, you'll know that this is the process of georeferencing, producing geotiffs, and so on. Those kinds of images is a process of pre-processing that takes place in most instances before we get the data. Also, there is some radiometric correction, typically that's applied before we receive the data. So this notion of pre-processing is something that we kind of live with, although at times we do have to do our own pre-processing, as we're finding out with some of the things that we're working with in Boone County. So this this slide runs through some of the different interactions that EMR goes through as it passes from the sun through the vacuum of space, interacts with the atmosphere, and then interacts with the Earth's surface. There's different things that can happen there, as we know, and then goes back through the atmosphere, again interacting with it, and finally reaches a remote sensor, probably operating in outer space, although not always. And again, in remote sensing, we do use the wave model of electromagnetic radiation, and this is it is electromagnetic because it's theorized as a set of two fluctuating waves that are normal to one another. They're the magnetic wave and the electric wave, which are normal and I guess out of sync or in sync with one another, but they're fluctuating in different planes, normal to one another. And so the sun, is the main source of EMR that we use in remote sensing, but we do use EMR from the Earth, the thermal energy that we look at. Typically, we have the most experience with channel 6 in Landsat Thematic Mapper. Is that is also a source of electromagnetic energy, because we're mostly looking at the Earth. Most of the EMR that we look at is reflected solar radiation, and so we use these Blackbody radiation curves to get a sense for a number of things, where certainly where the peak level of energy, the peak level of energy for a given object at a given temperature would be, at what wavelength would it be. And so you can see, there are several curves shown here: the sun, a tungsten filament, an 800 Kelvin red hot object, and a 300 Kelvin Earth, and then here's dry ice and liquid air. And you can see that the peak of these, each of these curves shifts to the right on this logarithmic wavelength scale, meaning, I guess, higher temperatures, more energy, and certainly higher frequencies, and shorter wavelengths for higher temperature objects. So the object that the hottest object that we normally consider is the 6,000 Kelvin sun. And so when you look at the atmosphere and what happens to this energy when it does strike the atmosphere, it is refracted. Refraction occurs as a result of the difference in the index of refraction between electromagnetic radiation that passes through the vacuum of space and passing through the atmosphere. It does slow down in the atmosphere. It does not travel at the quote-unquote speed of light. And it slows down quite a bit more in water, very substantially in water, although it's still going very fast. And so when you look at this graphic, you have several of the chemical components of a normal atmosphere that really make up much of the normal atmosphere, although nitrogen as a gas is not given here as a component, but one of the compounds of nitrogen, nitrous oxide, is given. And so you can think of these as accumulating their effects on the full atmosphere down here. So if we look at the effects of all of these gases, some of which are greenhouse gases, some are not, then this is the effect on the atmosphere. And so nitrous oxide, is a greenhouse gas. Oxygen and ozone. Ozone is a greenhouse gas, occurs in the high atmosphere and in the low atmosphere, much more harmful in the low atmosphere for public health. In the high atmosphere, helpful. So, and it is naturally occurring, and it also is human produced by human activity. Carbon dioxide, of course, that is naturally occurring and is also produced by human activity, although we believe there's a lot more of it being produced by human activity probably than certainly there has been historically. And water vapor, of course, is another major component of the atmosphere and has a great effect on our ability to see things through the atmosphere, the ability of radiation to pass through the atmosphere and to be used. So we use Wien's displacement law. This maybe refers better back to those Blackbody curves, but we use Wien's displacement law to knowing either the wavelength to calculate the temperature of an object that we're looking at with a remote sensor, or knowing the temperature of the object, then calculating what the peak wavelength of that, peak emittive wavelength of that body would be. Again, you guys did a great job with this. And so the radiant intensity of the sun, then, as we know, peaks in the visible, very convenient for us and our eyes. And, this is something that, really shapes a lot of what we do in remote sensing, is this characteristic or quality of solar radiation.